4.2 Double-Sideband Amplitude Modulation. Amplitude modulation is characterized by an information-bearing carrier amplitude AT, that is, a linear function of the baseband message signal MT. At the same time, the carrier frequency W and the phase B remain constant. We can assume B equals 0 without loss of generality. If the carrier amplitude A is made directly proportional to the modulating signal MT, then modulated signal is MT cos wet Fig. 4. 1. As we saw earlier, EQ 3.36, this type of modulation simply shifts the spectrum of MT to the carrier frequency, Fig. 4. La. Thus, if MT less than equals greater than MF, then MT cos 2 NFET less than equals greater than 1/2 MF plus FC plus MF G 4. 1. Recall that MF JC is MF shifted to the right by FC, and MF plus FC is MF shifted to the left by F. Thus, the process of modulation shifts the spectrum of the modulating signal to the left and to the right by FC. Note also that if the bandwidth of MT is BHZ, then, as seen from Fig. 4. LC, the modulated signal now has bandwidth of 2 BHZ. We also observe that the modulated signal spectrum centered at plus or minus JC, or plus or minus W, in radian per second, consists of two parts, a portion that lies outside plus or minus JC, known as the upper sideband, USB, and a portion that lies inside plus or minus JC, known as the lower sideband, LSB. We can also see from Fig. 4. LC that, unless the message signal MF has an impulse at zero frequency, the modulated signal in this scheme does not contain a discrete component of the carrier frequency FC. In other words, the modulation process does not introduce a sinusoid ATFE. For this reason it is called double-sideband suppressed carrier. Dsbsc modulation asterisk. The relationship of B to FC is of interest. Figure 4. LC shows that J-B, thus avoiding overlap of the modulated spectra centered at Fc and Fc. If Φ less than B, then the two copies of message spectra overlap and the information of MT is lost during modulation, which makes it impossible to get back MT from the modulated signal MT cos wet. Note that practical factors may impose additional restrictions on for instance, in broadcast applications, a transmit antenna can radiate only a narrow band without distortion. This means that to avoid distortion caused by the transmit antenna, we must have FAB1 B asterisk. The term suppressed carrier does not necessarily mean absence of the spectrum at the carrier frequency Fc. It means that there is no discrete component of the carrier frequency. This implies that the spectrum of the Dsbsc does not have impulses at plus or minus f, which also implies that the modulated signal MT cos 2 RRFCT does not contain a term of the form K cos 2 RRFCT, assuming that MT has a zero mean value. Figure 4. 1. Dsbsc modulation and demodulation. MT modulating signal. MT dash comma dash 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 single quote MT cos av MT to Fc MT cos ov 4.2 Double-Sideband Amplitude Modulation 143 cos rho taut carrier B MT cos ov modulated signal. A modulator -1 BB LSB 0 C2B blank cos WCF carrier E demodulator F I LMT 2 F broadcast band AM radio, for instance, with BE equals 5 kHz and the band of 550 to 1600 kHz for The carrier frequencies gives a ratio OFFC, B roughly in the range of 100 to 300. Demodulation. The Dsbsc modulation translates or shifts the frequency spectrum to the left and the right. BYF, i.e., at plus JC and JC, as seen from EQ. 4. 1. To recover the original signal MT from the modulated signal, it is necessary to retranslate the spectrum to its original position. The process of recovering the signal from the modulated signal, retranslating the spectrum to its original position, is referred to as demodulation. Observe that if the modulated signal spectrum in Fig. 4. LC is shifted to the left and to the right BYFC, and multiplied by 1/2, we obtain the 1.4 amplitude modulations and DEMODULATIONS. Spectrum shown in Fig. 4. LD, which contains the desired baseband spectrum plus an unwanted spectrum at plus or minus 2 Fc, the latter can be suppressed by a low-pass filter. Thus demodulation, which is almost identical to modulation, consists of multiplication of the incoming modulated signal MT coswet by a carrier coswet followed by a low-pass filter, as shown in Fig. 4. 1e. We can verify this conclusion directly in the time domain by observing that the signal ET in Fig. 4 is ET equals MT cos 2 wet 1 equals to MT plus MT cos 2 WCT. Therefore, the Fourier transform of the signal ET is I1 E F equals 2 M F plus 4 M F plus 2 Phi plus M F 2 G 4.2 A 4.2 B. This analysis shows that the signal ET consists of two components, 1/2 MT and L2 MT cos 2 WCT, with their non-overlapping spectra as shown in Fig. 4. LD. The spectrum of the second component, being a modulated signal with carrier frequency 2 Fc, is centered at plus or minus 2 Fc. Hence this component is suppressed by the low-pass filter in Fig. 4. LE. The desired component, L2MF, being a low-pass spectrum, centered ATF equals 0, passes through the filter unharmed, resulting in the output 1/2 MT. A possible form of low-pass filter characteristics is shown, under dotted line, in Fig. 4. 1D. The filter leads to a distortionless demodulation of the message signal MT from the Dsbsc signal. We can get rid of the inconvenient fraction 1/2 in the output by using a carrier to coswet instead of coswet. In fact, later on, we shall often use this strategy, which does not affect general conclusions. This method of recovering the baseband signal is called synchronous detection, or coherent detection, where we use a carrier of exactly the same frequency and phase as the carrier used for modulation. Thus, for demodulation, we need to generate a local carrier at the receiver. In frequency and phase coherence, synchronism, with the carrier used at the modulator. Example 4. 1 for a baseband signal. MT equals cos WMT equals cos 2 RRFMT. Find the Dsbsc signal, and sketch its spectrum. Identify the USB and LSB. Verify that their Dsbsc modulated signal can be demodulated by the demodulator in Fig. 4. The case in this example is referred to as tone modulation because the modulating signal is a pure sinusoid, or tone, cos WMT. To clarify the basic concepts of Dsbsc modulation, we shall work this problem in the frequency domain as well as the time domain. In the frequency domain approach, we work with the signal spectra. The spectrum of the baseband signal MT equals cos WMT is given by 1. F equals 2 O F FM plus O F plus FM L equals RR O W WM plus O W plus WM. Figure 4.2. Example of Dsbsc modulation. 4.2 Double-Sideband Amplitude Modulation 145. The message spectrum consists of two impulses located at plus or minus 1 meter, as shown in Fig. 4.2a. The Dsbsc modulated spectrum as seen from EQ. 4.1 is the baseband spectrum in Fig. 4.2 are shifted to the right and the left by La times 1/2 as shown in Fig. 4.2b. This spectrum consists of impulses at angular frequencies plus or minus UC, Lm, and plus or minus UC plus Lm. The spectrum beyond La is the USB, and the one below La is the LSB. Observe that there Dsbsc spectrum does not have the component of the carrier frequencile. This is why it is called suppressed carrier. In the time domain approach, we work directly with signals in the time domain. For the baseband signal MT equals cos WMT, the Dsbsc signal Dsbsc is Dsbsc equals MT cos wet. This shows that when the baseband message signal is a single sinusoid of frequency Lm, the modulated signal consists of two sinusoids, the component of frequencile plus Lm, the USB, and the component of frequencile Lm, the LSB. Figure 4.2b shows precisely the spectrum of less than P0 SASC T. Thus, each component of frequency Lm in the modulating signal turns into two components of frequencies L plus Lm and Lm in the modulated signal. Note the curious fact that there is no component of the carrier frequency La on the right-hand side of the preceding equation. As mentioned, this is why it is called double-sideband. Suppressed carrier Dsbsc modulation. We now verify that the modulated signal Dsbsc equals cos WMT cos wet when applied to the input of the demodulator in Fig. 4. La yields the output proportional to the desired baseband signal cos WMT. The signal ET in Fig. 4. La is given by 2fc ET equals cos WMT cos 2 wet 1 USB LSB equals 2 cos WMT 1 plus cos 2 WCT MF LI 1 DSB spectrum I 114 1/4 A, F, B, LSB, LR USB, F, F, C, 1/8, I, 1/8, 2FC1/4.6 amplitude modulations and DEMODULATIONS. Figure 4.3. Nonlinear. Dsbsc. Modulator. The spectrum of the term cos WMT cos 2 WCT is centered at 2 WC and will be suppressed by the low-pass filter, yielding 1/2 cos WMT as the output. We can also derive this result in their frequency domain. Demodulation causes the spectrum in Fig. 4.2b to shift left and right by W and to be multiplied by 1/2. This results in the spectrum shown in Fig. 4.2c. B. Low-pass filter suppresses the spectrum centered at plus or minus 2 W, yielding the spectrum 1/2 mJ. Modulators. Modulation can be achieved in several ways. We shall discuss some important categories of modulators. Multiplier modulators. Here modulation is achieved directly by multiplying MT with cos-wet, using an analog multiplier whose output is proportional to the product of two input signals. Typically, such a multiplier may be obtained from a variable gain amplifier in which the gain parameter, such as the F3 of a transistor, is controlled by one of the signals, say, MT. When the signal cos-wet is applied at the input of this amplifier, the output is proportional to MT cos-wet. In the early days, multiplication of two signals over a sizable dynamic range was a challenge to circuit designers. However, as semiconductor technologies continue to advance, signal multiplication ceased to be a major concern. Still, we will present several classical modulators that avoid the use of multipliers. Studying these modulators can provide unique insight. And an excellent opportunity to pick up some new signal analysis skills. Nonlinear modulators. Modulation can also be achieved by using nonlinear devices, such as a semiconductor diode or a transistor. Figure 4.3 shows one possible scheme, which uses two identical nonlinear elements boxes marked Ni. Let the input-output characteristics of either of the nonlinear elements be approximated by a power series. Y t equals at x t plus bx2 t 4.3, where x t and y t are the input and the output, respectively, of the nonlinear element. B. Summer output Z t in Fig. 4.3 is given by Z t equals y t, y z t equals x e t plus bx t a x2 t plus bx z2 t. Substituting the two inputs 11 t equals cos wet plus m t and x2 t equals cos wet m t in this equation yields Z t equals 2a m t plus 4b m t cos wet. The spectrumo FM T is centered at the origin, whereas the spectrumo FM T cos wet is centered at plus or minus W. Consequently, when Z T is passed through a bandpass filter tuned to W, the signal AM T is suppressed and the desired modulated signal 4B M T cos wet can pass through there. System without distortion. M T x1 T y T Ni Z T BPF plus or minus FFIC 4B M T cos FFIC T Ni X2 T Y2 T 4.2 Double-Sideband Amplitude Modulation 147. In this circuit there are two inputs, M, T, and cos wet. The output of the last summer, Z, T, no longer contains one of the inputs, the carrier signal cos wet. Consequently, the carrier signal does not appear at the input of the final bandpass filter. The circuit acts as a balanced bridge. For one of the inputs, the carrier. Circuits that have this characteristic are called balanced circuits. The nonlinear modulator in Fig. 4.3 is an example of a class of modulators known as balanced modulators. This circuit is balanced with respect to only one input, the carrier. The other input M, T, still appears at the final bandpass filter, which must reject it. For this reason, it is called a single balanced modulator. A circuit balanced with respect to both inputs is called a double-balanced modulator, of which the ring modulator, see later, Fig. 4.6, is an example. Switching modulators. The multiplication operation required for modulation can be replaced by a simpler switching operation if we realize that a modulated signal can be obtained by multiplying mt, not only by a pure sinusoid but by any periodic signal sent t of the fundamental radian frequency we. Such a periodic signal can be expressed by a trigonometric Fourier series as 00 P(t) equals LCN cos NCVET plus 0 N 4.4 N equals O. Hence 00 mt less than pt equals LCN mt cos NCVCT plus 0 N 4.4 b. N equals O. This shows that the spectrum of the product mt less than pt is the spectrum mCV shifted to plus or minus EV plus or minus 2 CVC plus or minus NCVC. If this signal is passed through a bandpass filter of bandwidth 2Bhz and tuned to E, then we get the desired modulated signal C1mt cos wet plus 01 asterisk. The square pulse train WT in Fig. 4.4b is a periodic signal whose Fourier series was found earlier by rewriting the results of example 2.4 as WT equals minus 21 plus IT2 cos wet minus 31 cos 3 CVET plus 5 to 1 cos 5 CVCT. The signal MTWT is given by MTWT equals MT plus MT cos wet MT cos 3 CVCT plus MT cos 5 CVCT. 21 at 231.51. 4.5 4.6 The signal MTWT consists not only of the component MT, but also of an infinite number of modulated signals with carrier frequencies EV 3 CVC, 5 CVC. Therefore, the spectrum of MTWT consists of multiple copies of the message spectrum MF shifted to 0 plus or minus JC plus or minus 3 FC plus or minus 5 FC. With decreasing relative weights, as shown in Fig. 4.4c. For modulation, we are interested in extracting the modulated component MT cos wet only. To separate this component from the rest of the crowd, we pass the signal MTWT through a bandpass filter of bandwidth 2Bhz, or 4 ITB radian per second, centered at the frequency plus or minus JC, provided the carrier frequency FC2B, or WE4ITB. This will suppress all the spectral components not centered at plus or minus JC to yield the desired modulated signal. 2. It MT cos wet Fig. 4.4d. We now see the real payoff of this method. Multiplication of a signal by a square pulse train is in reality a switching operation in which the signal MT is switched on and off periodically. It The phase O1 is not important. 1.4.8 amplitude modulations and DEMODULATIONS. Figure 4.4. Switching modulator for Dsbsc. MT WT NN side phase T WT A B C 0 I 0 I J 1 Q R minus 2 meters JC T cos wet I underscore band per filter S blank FL R full F D HTJ plus T1 T plus percent J plus TR TI plus JAH1 Y minus 1 plus 1 R J can be accomplished by simple switching elements controlled by WT. Figure 4.5 shows one such electronic switch, the diode-bridge modulator, driven by a sinusoid A cos wet to produce the switching action. Diodes D1, D2 and D3, D4 are matched pairs. When the signal cos wet is O for polarity that will make terminal C positive with respect to D, all the diodes conduct. Because diodes D1 and D2 are matched, terminals A and B have the same potential and are effectively shorted. During the next half cycle, terminal D is positive with respect to C, and all four diodes open, thus opening terminals A and B. The diode bridge in Fig. 4.5a, therefore, serves as a desired electronic switch, where terminals A and B open and close periodically with carrier frequency FC when a sinusoid A cos wet is applied across terminal C and D. To obtain the signal MT/WT, we may place this electronic switch terminals A and B in series Fig. 4.5b, or across in parallel MT, as shown in Fig. 4.5c. These modulators are known as the series bridge diode modulator and the shunt bridge diode modulator, respectively. This switching on and off of MT repeats for each cycle of the carrier, resulting in the switched signal MT/WT, which, when bandpass filtered, yields the desired modulated signal 2nMT cos wet. Another switching modulator, known as the ring modulator, is shown in Fig. 4.6a. During the positive half cycles of the carrier, diodes D1 and D3 conduct, and D2 and D4 are open. Hence, terminal AA is connected to C, and terminal B is connected to D. During the negative half cycles of the carrier, diodes D1 and D3 are open, and D2 and D4 are conducting, thus connecting terminal A to D and terminal B to C. Hence, the output is proportional to MT during the positive half cycle and to MT during the negative half cycle. In effect, MT is multiplied by a square pulse train WT, as shown in Fig. 4.6b. The Fourier series for WT can be found by using the signal WT of EQ. 4.5 to yield WT equals 2WT1. Therefore, we can use the Fourier series of WT EQ. 4.5 to determine the Fourier series of WT as WT equals N4 cos wet minus 31 cos 3 WCT plus minus 5 L cos 5 WCT. 4.7a. Figure 4.5. A. Diode bridge. Electronic switch. B. Series bridge. Diode modulator. C. Shunt bridge. Diode modulator. Figure 4.6. Ring modulator. MT. A. AB. C. Plus. 4.2 Double-Sideband Amplitude Modulation 149. A cos ULCF. A. Plus. Band passer. Filter kilometer T cos OVM TL. Band pass. B. Filter kilometer T cos OV. BL CL. Band pass. Filter kilometer T cos wet. Plus. A. W0 T. NNNNN ULF UUUUUUUUUUUNNNNNNNR. B. Q N vid equals M T I 1 N WO T N N I N I plus Julia Whippeal Dual 1 C D 150 amplitude modulations and DEMODULATIONS. Hence we have Vi T equals M T WO T equals 4 M T cos wet M 31 T cos 3 wet plus minus 51 meters T cos 5 wet. 4.7b. The signal M T WO T is shown in Fig. 4.6d. When this waveform is passed through a bandpass filter tuned to WE, Fig. 4.6 at the filter output will be the desired signal, 4 M T cos wet. In this circuit there are two inputs, M T and cos wet. The input to the final bandpass filter does not contain either of these inputs. Consequently, this circuit is an example of a double balanced modulator. Example 4.2 frequency mixer or converter. Figure 4.7. Frequency mixer or converter. We shall analyze a frequency mixer or frequency converter used to change the carrier frequency of a modulated signal MT cos wet from WE to another frequency WJ. This can be done by multiplying MT cos wet by 2 cos WA mixed, where WMX equals WE plus WJ or WE WJ, and then bandpass filtering the product as shown in Fig. 4.7a. I 0 I XT bandpass filter tuned to Y 2 cos WE plus or minus W1 T A dash dash comma I dash comma backslash I backslash I Wisconsin 2WC Y2WC B. The product XT is xt equals 2 meters t cos wet cos wa mixed dash single quote w 2 w c plus w1 equals m t cos w w mixed t plus cos w plus w mixed t. If we select w mix equals w w1, then xt equals m t cos wit plus cos 2 w w1 t. If we select w mx equals w plus wj, then xt equals m t cos wit plus cos 2 w plus wj t. In either case, as long as we w1 to 27b and w1 to 2 RRB, the various spectra in Fig. 4.7b will not overlap. Consequently, a bandpass filter at the output, tuned to W1, will pass the term mt cos yt and suppress the other term, yielding the output mt cos wit. Thus, the carrier frequency has been translated to WR from W.4.3 amplitude modulation, AM151. The operation of frequency mixing, conversion, also known as heterodyning, is basically a shifting of spectra by an additional WMX. This is equivalent to the operation of modulation. With a modulating carrier frequency, the mixer oscillator frequency WMX that differs from the incoming carrier frequency by Wj, any one of the modulators discussed earlier can be used for frequency mixing. When we select the local carrier frequency WMX equals W plus W1, the operation is called upconversion, and when we select WMX equals Wj, the operation is downconversion. Demodulation of Dsbsc signals. As discussed earlier, demodulation of a Dsbsc signal essentially involves multiplication by the carrier signal and is identical to modulation. See Fig. 4.1. At the receiver, we multiply the incoming signal by a local carrier of frequency and phase in synchronism with the incoming carrier. The product is then passed through a low-pass filter. The only difference between the modulator and the demodulator lies in the input signal and the output filter. In the modulator, message MT is the input while the multiplier output is passed through a bandpass filter tuned to W, whereas in the demodulator, the Dsbsc signal is the input while the multiplier output is passed through a low-pass filter. Therefore, all the modulators discussed earlier without multipliers can also be used as demodulators provided the bandpass filters at the output are replaced by low-pass filters of bandwidth B. For demodulation, the receiver must generate a carrier in phase and frequency synchronism with the incoming carrier. These demodulators are synonymously called synchronous or coherent, also homodyne, demodulators. Exam PLE 4. 3. Analyze the switching demodulator that uses the electronic switch diode bridge, in Fig. 4.5a. As a switch, either in series or in parallel. The input signal is MT cos Vt. The carrier causes the periodic switching on and off Fourier input signal. Therefore, the output is MT cos Vt x Wt. Using the identity cos x cos y equals 0.5 cos x plus y plus cos x, y, we obtain mt cos Vt x Wt equals mt cos Vt plus cos Vt, ICOS 3 Vt plus 2. equals mt cos 2vt plus terms of the form mt cos nwct. Junior 1 equals mt plus mt cos 2wct plus terms of the form mt cos nwct. Junior spectra of the terms of the form mt cos nwet are centered at plus or minus nwc and are filtered out by the low-pass filter, yielding the output 1 nmt. It is left as an exercise for the reader to show that the output of the ring circuit in Fig. 4.6 are operating as a demodulator, with the low-pass filter at the output is 2 nmt, twice that of the switching demodulator in this example.